All right, welcome back. We're nearing the end of our first week, so we have our first sort of question and catch-up day. There's a few slides from lecture 3 that I didn't get to cover, so we're gonna go over those first, and then I'll open it up to questions from the live students because I don't see anyone posting anything on Piazza. And barring that, I figure I'll just go over a few of the exercises in the book that I thought were interesting, just to give you some more exposure to my thought process in modeling some of these problems. Now I said that the project would be up yesterday. Unfortunately, I was looking over it again, thinking about how exactly I wanted you all to do it, and it just wasn't. The problem wasn't working out. It was uninteresting and too bloated, and ultimately I need to rethink it a little bit. So I'm now hoping to post it on Saturday. I still want to get it to you guys as early as possible, but it needs some retooling. I neglected to come up with a reading quiz for tomorrow's reading, so you guys are off the hook for that. I still recommend reading the section, but there was not a reading quiz for it. Homework 3 should still go up today sometime, and I think that's it. Um, if anyone has any exercises from the book or somewhere else that they wanted me to discuss in the back portion of this lecture, go ahead and post them in the chat, and I'll be sure to give those an attempt live here. So, like I said, there was a few slides from lecture 2 that I did not get to cover. So I'll start with those. So we covered this slide talking about what a graph is, but there are some graph theory sort of problems that I didn't cover. So one extra definition, and this is a common idea within graphs, is the idea of a bipartite graph. And that's a graph that we can split the vertices into two groups such that all of the edges start in one group and end in another group. This is commonly used to model sort of web search algorithms. So Google and Bing and etc. They can all be modeled as bipartite graphs. Social medias as well. Scheduling and placement problems, and a lot of sort of shipping and logistics problems are modeled using bipartite graphs. And these are nice because there are not a lot of neat results that are exclusive to bipartite graphs. So we can exploit those to make some of our problems sort of easier. So be on the lookout for those sorts of things. And the book talks about matching problems. So I wanted to run through an example of a matching problem. So if we have a graph, yeah, there we go. If we have a graph with vertices and edges, then a matching is a set of edges such that every vertex on the graph is incident to one of our selected edges. So incident just means that an edge and a vertex connect, right? So this vertex is incident to this edge, and this edge is incident to this vertex because they touch. So a perfect matching is a matching where every vertex is incident to exactly one edge in S. And let's suppose we have weights for our edges. We want to formulate the problem of finding a perfect matching with the minimum total weight as an IP. So let's just do an example of a perfect matching on our graph here. We'll select that edge. We'll select that edge. Did I miss a vertex from my example? No, I duplicated one. There we go. That edge, this edge, and this edge. See how all of our vertices are in that set exactly once. That's a perfect matching. This is useful for supply chain type things. Dating apps are perfect matchings. A whole slew of things. So we want to think about these as an IP. So we're going to let x equal 1 if edge E is in S and 0 otherwise. So this is similar to this, we're just looking at every edge and saying, is this in S or is it not? So this is for all edges in the set of edges. So I've had a little bit of questions about what some of these symbols mean, and I'm planning on releasing a cheat sheet about sort of mathematical symbols. But this inverted A is for all or for every, and this sort of crunched epsilon or E is an element of. So that just says E is an element of E, or maybe better, is in. So we use that for an element of a set. And then we need a definition, another new part from graph theory. Define the neighborhood of V to be the set of edges incident to V. So if V is this vertex, then its neighborhood is these edges. Sometimes people will use the neighborhood to indicate the nodes at the far end of those edges. So that would be the nodes that are adjacent to our first node, to V. So if this is V, then the purple is delta V. The neighborhood. So we can think about this matching problem as saying that for every vertex, exactly one of the edges in its neighborhood should be in S. And we can do this two different ways. First is, I guess, fairly straightforward. We want to minimize, so we have the want to minimize the weight of our selection, right? So this is for every E, for every edge, the weight of that edge times whether or not that edge is in S, such that given, so for every vertex, the edge, or and every edge in the neighborhood of that vertex, xe equals 1. So for every vertex, exactly one of the elements of the edges in that vertex's neighborhood should equal 1. And of course, this is a binary variable. For all edges. So that's the first way, but we can reinterpret this a little bit. And let's look at our example graph. I'm going to call this A, B, C, D, E, F, G, and H. So that's the labels on our nodes. And then for our edges, I'm going to label these 1, 2, 3, 4, 3, 4. Oop. Crap. 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then we're going to create what's called an incidence matrix. So if each row is a vertex, and each column is one of the edges, I might not have enough room here. Touch too many things. 5, 6, 7, 8, 9, 10. 10 edges. And we're going to put zeros in most of the spots and ones wherever the edge is incident to that vertex. So 1 is incident to A and B. 2 is incident to A and F. 3 runs between C and B. 4 runs between C and D. 5 runs between D and E. 6 runs between E and F. And G, 7 is F and H. No, 7 is not F and H. 7 is D and H. 8 is F and H. 9 is F and G, and 10 is G and H. And pretend everything else there is a 0. Now what we want is a selection of vertices, of edges, such that each vertex is incident to exactly one edge that we've selected. Now if we place the word, now that we have this incidence matrix, this looks like a problem we've done before. This is, does anyone have any ideas? Set covering. It's the set covering problem. Right, because we're selecting edges. The edges here are our columns, so in effect we're selecting columns such that an edge, or such that each row or vertex is covered, is incident to one of those columns, to one of those edges. So if we look at our perfect matching that I have drawn earlier, we picked 2, 3, 5, and 10, right? So that covers A, covers B, C, D, E, F, G, and H. And more than that, it covers them all exactly once. So this perfect matching problem is actually equivalent to the set partition problem. If we're looking for an imperfect matching, that is the same as the set covering. But the perfect matching is the same as a set partition problem that you did in the homework. So this is an example of a graph theory problem that is the same as a classic integer programming problem, where we can use integer programming to solve it just fine. But there do exist graph theory exclusive algorithms for finding these things, for finding perfect matchings quickly. Um, this problem has a, a property called tonal unimodularity, which you don't need to worry about, but it means that the IP, if we relax it to an LP, it will give us an integer solution every time. You don't need to know that yet, but so for this problem, solving it as an integer program or as a graph theory problem, it doesn't matter so much. Both can be done quickly. But there are many network problems, many graph theory problems that can be formulated as IPs, but require many, many constraints and may not be totally unimodular. So they may not give us integer solutions every time. Some of these problems have graph theory algorithms that run very quickly. So it's important to recognize when we can express certain problems as graphs and whether or not those problems will be faster to solve with graph theory than they are with integer programming. So maybe the best example of this is the shortest path problem, which the book discussed. But the shortest path is exactly what it sounds like. If we have a graph, and we want to sort of travel from one node, S, to another node, T, we want to maybe pick the shortest path. So an ST path is just a sequence of edges that if we follow that sequence, it'll get us from S to T. There are a variety of formal ways to define that, but that's kind of the intuitive way. A minimum length ST path, also known as the shortest path, is an interesting problem, and we can model it as an IP, but we're going to see that it takes many, many constraints. So, well, it's the shortest path, so we just want to minimize oh, I guess I should define my variables. Let's define the same way as last time. X E is 1 if edge E is in the path and 0 otherwise. For every edge in E. And all we want to do is minimize the total number of edges we pick. You could include a weight on the edges. That's totally doable, and rather common, in fact. But for our example, I don't want to bother. I just want to use the least number of edges. So that could be more. So if you were trying to walk in a city from one point to another, um, those roads or paths that you're on might have different lengths, and so you might care about the length of that path, and you could include that in your objective function. Say you're trying to send a signal from one website to another. Maybe the distance between those sort of maybe not websites but servers. The distance between the servers maybe doesn't matter as much as the downtime at each server, and so you care more about using fewer paths than using fewer edges maybe than using um, a sort of shorter edges. And we want to make sure that our vector x represents a st path. That's what we want. But how do we do that? Well, we need to define a new sort of graph theory tool. Let's say we have a subset of edges. By the way, this symbol means subset. It just means that Q has some of the edges in our set of edges. That subset is an st cut if every st path must contain an edge in Q. So I'm going to throw up a few examples of st cuts on this graph. Obviously, if we remove all of the edges around S, there's no more path from S to T. If S is isolated, we can't get to T. So that's an example of one. What if we remove these two edges? That's another cut, right? An ST cut doesn't even have to be minimal, right? We could remove more than just the two edges. We could remove all four of these, or even we could remove even all of the edges, and that would be a valid ST cut. So we can use this to represent to formalize our sort of constraint here. So we want to yuck minimize our path length such that every ST cut has at least one of its edges used. So for every ST cut Q. So what does that mean? So if we come up here, let's look at our 3 Qs right now. Our ST path uses one of the edges in the red Q. Uses one of the edges in our yellow Q and 2 of the edges in our green Q. It would be impossible for us to draw an ST cut that did not include one of the edges in our path that we've drawn here. And that just comes from the definition of the ST cut. Every ST path must contain an edge in any cut. Now, I'm throwing around a lot of terminology here, and I hope some of it is clear enough. But we can sort of invert that definition to say that every path must use an edge in every single possible cut. I'm not going to that's the idea. We can invert this definition and say that a path X must use at least one edge from every valid ST cut. Yeah. So this constraint is just enforcing that. So x of e must be greater than 1. The sum of the edges in every cut must be at least 1. We have to use at least one edge from every cut to make a path. And of course, we need to say that x is binary. I'm going to use this notation this time for fun. This is the cardinality. And that's just the number of things in E. So translating this just means that we have an x sub E for everything in E. So each of those has to take a value 0, 1. In other words, our vector has length cardinality of E, and it needs to be each element or each entry in that vector needs to be either 0 or 1. So the problem with this formulation is that there are something like 2 to the, let me use a different color. There. Maybe 2 to the cardinality of v minus 1 st cuts. Now, 2 to the v minus 1 is enormous for a large v, for a large number of vertices. Should that be a v? I have v written down. Is that true? Seems like it should be in terms of edges. I don't think the book says. It is actually edges. I was looking at vertex cuts instead of edge cuts when I looked this up the first time. So it is actually number of edges. Still a very large number. Even larger, perhaps, than number of vertices. If you take DOR2 in the fall, or we will discuss sort of what these. We'll discuss more about the size of problems and what that means for how fast we'll be able to solve them. But an IP of that size is going to be very slow to solve in general. However, as we'll discuss later in the class, there are very fast algorithms for running running shortest path problems, finding shortest paths. And so if your problem ends up being a shortest path, you may want to think about translating it to graph theory and using one of their algorithms to solve this quickly. So that's the important part of this sort of part of the lecture. Think about graphs. Think about if your problem can be a graph. Because it might just be faster to solve. Anyway, that is all I have for this part of today. So we can move on to questions. If anyone has an exercise in the book or a question from something else that they'd like me to talk about, go ahead and speak up or post it in the chat. Otherwise, I'll pull some exercises out myself. All right. Well, I'll keep an eye on the chat, and I'll find one of the problems that I liked. Let's do this number 5. So this is 1.2.5. So I'm gonna solve this one in front of you guys. If you wish to find out how to pack crates on a transport plane in an optimal way, the crates are of 5 possible types, A, B, C, D, and E. For each crate type, the next table gives its weight, its volume, and its value. The transport plane is divided into 3 segments, front, middle, and back. Each segment has a limited volume and the limit on the weight of the cargo in that segment. So we have the weight of the crates, the volume of the crates, the value of the crates, the volume capacity of the 3 cargo holds, excuse me, and the weight capacity of the 3 cargo holds. So I'm going to start, I think, by formulating this first part of the problem as an IP, and then move on to the second half. Pulled up my book. I wish I could have. I'll just tack on an extra page. Here, right below the problem. That way I can reference it. So we have 5 crates. And we have 3 cargo holds. Front, middle, and back. And so what we want to do is assign crates to these cargo holds. So if we think about the assignment problem, that's in the book, 1.3.1, they use this variable, xij 1 to 0, if I is assigned to j, 0 otherwise. You get the idea. Now the difference between the assignment problem and this problem, one of the differences, is that in the assignment problem, an employee could only be assigned one job. Or I guess, yes, they could only be assigned once. Here we have multiple of each crate. So instead of this, we're going to let xij be the number of type I crates assigned to hold j. Right? So then we need to think about our constraints. Each hold has a volume and a weight capacity. So those are constraints, right? We can't breach the volume, the maximum volume or maximum weight of either one. So let's think about those. We need something that says volume this of crates in hold j is less than or equal to the volume capacity of hold j. For the sake of being being succinct, or sort of not having to write a million constraints here, I'm going to define some vectors. So I'm going to call this capacity volume. I'm going to call this capacity weight. These two vectors. And I'm going to call this just volume and weight and we need something for value. We've already used C. I'm just going to write D. It's a dollar value. So the volume of crates in hold J is going to be volume of I times so the volume of crate type I times the amount of crate type I that is in the hold we're looking at, hold J. Then we're going to sum this up for all I in right, for all of our I. So I is in A, B, C, D, E, and J is in F, M, B. So I is our crate, and J is our hold, front, middle, back. So for all I, we're going to sum up this, right? Volume times the number of crates. And we can simplify, or maybe condense this notation to just be some vector notation. The volume times the amount of crates in J. We keep our J subscript here. And then this has to be less than or equal to the volume capacity of hold J. So the C sub V sub J. If that makes any sense. So C sub V J is going to be our available volume, hold, the front hold, the middle hold, and the back hold. So the sub J there would be picking out specific ones of these. And this is for all J. Move that closer. So this, so this statement is this and this. And this statement is this. Now, we also had a weight capacity. So I'm going to go ahead, and I think it's probably no surprise that the weight capacity constraint is going to be very similar in structure to the volume capacity constraint. So we have the weight of each crate times the number of crates in the hold, less than or equal to the weight capacity of that hold for all three holds. So those are our first two constraints. And then we had a second page for this problem. To keep the plane balanced, we need to satisfy the following constraints. The weight of the middle cargo needs to be at least as big as the weight of the front cargo plus the weight of the back cargo. So let's do that first. Well, we've already have the weight of cargo in hold J. So all we need to do is adapt this to say that the weight of the middle cargo submiddle is greater than or equal to the weight of the rear cargo plus the weight. My drawing tablet is having a bad time today. Of the front cargo. That's it. And then the weight of the middle cargo should be less than or equal to twice the weight of the front cargo times the weight of the back cargo. So I'm just going to duplicate that. Whoops. Twice. And then this should be less than or equal to. And then we have a limit on the number of crates of each type. So that's going to be, I'm just going to define this vector L is going to be 12, 22, 15. I missed one. 8. I missed an 8. 8, 22, 15, and 11. So that's going to be the limit on number of crates that we can pack. And these constraints should be, no, we have all of our subscripts defined, so we don't need to include a for all statement for either of these. These are just single constraints. Whereas these constraints were true for all 3 cargo holds, this already incorporates all 3 cargo holds. But our limit so within, okay, so we only have L number of each type of crate. But we're packing the crates into 3 different holds. So we need to sum up over all J over all of the holds. It should be less than or equal to L of I for all I. And then, of course, we need our integer constraint. The vector x is in the integer, the 5 integer lattice. So that's our constraints. I didn't do our objective yet, but I think it's not terribly difficult to see that it's just going to be the value, D, transpose the value of each crate, transpose the amount of each crate, and then we need to sum it up sum this up for every cargo hold. This has gotten a bit congested. So there we go. That's that problem as an IP. Does anyone have a question or concern about what I've done here? Is everyone understanding all of the vector multiplication that I have scrawled here on this page? Great. I could try to do another problem, but I feel like that might just be me rambling on about something for a while. So I think unless anyone has any other questions or requests, we can be done for today. Alright, I'll stick around for a little while. You guys are free to go.